Some people think math is all about the numbers. I'm here to show you that it's actually not. Math is so much more than that. It's the natural language of the universe. Aside from that, math is also just plain beautiful. And my goal today is to give you a glimpse into topics such as groups, symmetries, Lie groups, Lie algebras, vector fields, and sheaves. Topics that really a lot more people should know about. I also hope to be able to show you the beauty of these topics. And while we won't be going into a lot of the notation and rigorous definitions, I want you to leave this video with a feel for these topics. Note that an understanding of elementary linear algebra will be required to understand some concepts. But before we can begin to explore this wonderful world of math, we have to understand mathematical objects called groups. We can consider the group of symmetries of this square. What is a symmetry? Right now we have our default position, which we'll define as a 0-degree rotation with the red dot on the lower right. Consider rotating our square 90 degrees. Except for that dot as a reference, the square looks the same, right? This is a symmetry of that square. Rotate the square another 90 degrees. The total rotation is now 180 degrees. Turns out that if we rotate by any multiple of 90 degrees, the square looks the same. If we rotate another 180 degrees, we get a square with the original position of the red dot. This 360-degree rotation is the same as the 0-degree rotation, which is the identity element of this group. If we rotate by any more than this, we have positions of the red dot that correspond with the set of 0-degree, 90-degree, 180-degree, and 270-degree rotations. So the set of our rotations is 0, 90, 180, and 270. A group also has a certain quote-unquote arithmetic. That is, you can take two elements of a group and produce a third. For example, rotating by 90 degrees and then by 180 degrees corresponds to rotating by 270 degrees, which just corresponds to adding 90 plus 180 equals 270 degrees. Adding the identity element and another element just results in the element. That's how we define the identity element of a group. In this case, this group is what we call abelian, meaning that this addition is commutative. This means that rotating by 90 degrees and then by 180 degrees is the same thing as rotating by 180 degrees and then by 90 degrees. We can also represent this using addition. 90 plus 180 equals 180 plus 90. Some figures have an infinite set of symmetries. Consider this circle. No matter by what amount you rotate it, this circle looks the same. The set of symmetries of this circle is what we call a Lie group. This particular Lie group is denoted by SO2, the group of rotations of a circle embedded in two-dimensional Euclidean space. A Lie group is a continuous group that is also a differentiable manifold. Now, what is a manifold? A manifold is defined as a topological space that locally resembles Euclidean space at every point. Examples of Euclidean space are like a line, a plane, 3D space, so on and so forth. For example, a circle is a manifold, and so is a sphere. Even a plane itself is a manifold. This weird thing is also a manifold. What that complicated definition is basically saying is that if you zoom in on a point to an infinitely small magnitude, you'll get something that looks like a plane, or at least a tiny section of it, if the manifold is a surface embedded in 3D space. If these conditions are not met, it'll resemble Euclidean space with some other dimensionality. Now, to be clear, the manifold shown is not a Lie group, since it only has one symmetry, the identity. Now consider our circle again. Every Lie group has a corresponding Lie algebra. A Lie algebra is basically defined as the tangent space to the identity element of a Lie group. Consider the circle we've been using. Its Lie algebra is the tangent line to the red point, which is what we are using to represent the identity element of the Lie group. A sphere's rotation group, denoted by SO3, has two different types of rotations. Rotations on the quote-unquote horizontal unit circle or on the quote-unquote vertical unit circle. Mathematicians, in fact, call it two-dimensional because on the sphere, you only need the two parameters to describe exactly where you are on it, i.e. the two angles. The identity element is basically a 0-degree rotation horizontally and a 0-degree rotation vertically. This defines a single point on the surface of the sphere, the Lie algebra of which is a tangent plane to the point of the sphere with both rotations at 0 degrees. A Lie algebra, in fact, is a vector space, because it is a tangent space, which is a type of vector space. This vector space over a field of numbers f is usually denoted by G, with a special font, of course, as is customary in math. A Lie algebra also has an operation called the Lie bracket. For example, for the vector space of three-dimensional vectors, also known as R3, the Lie bracket is defined as the cross product of two vectors, where we can create a new vector from a pair of two vectors. This is similar to addition, and in fact, Lie algebra is another example of a group. You might see notation like this if you look up Lie brackets. What this is basically saying is that it's defining an operation that takes two vectors, aka two parts, defined more abstractly, each coming from the same vector space G and producing a third vector. This is basically the Lie bracket of Lie algebra, and for the vector space we were talking about earlier, it is the cross product, and defining the Lie bracket as the cross product is written like this, where the x and y are two elements of the Lie algebra. The Lie bracket describes a sort of arithmetic of the group that is the Lie algebra. As Alamy is saying, from now on, we're going to have to use linear algebra a lot. So if you're not comfortable with it, I suggest you brush up on some topics before continuing to watch. That warning aside, let's get back to the concept of a vector space. And even if you know what it is, this part of the video should be a good review of some concepts about them, because these concepts will be key later on. A vector space is defined using its two basis vectors, and every vector in the vector space can be defined as a weighted sum of the basis vectors. What this means is that if you have two basis vectors, I hat and j hat, then every other vector in that vector space can be written as some constant times I hat plus some constant times j hat. If we want to define a three-dimensional vector space, we just need three basis vectors, which we can call I hat, j hat, and k hat, and so on in higher and higher dimensions. We might run out of letters though, which is why mathematicians sometimes use the notation e sub 1 to e sub n for n-dimensional spaces. We can define a sort of arithmetic of vector spaces. Adding vector spaces is what we call a direct sum of vector spaces. To define how this works, let's look at the direct sum of two vectors first. For example, if we have a vector 1, 2, 3 and a vector 4, 5, where 1, 2, 3 is in R3 and 4, 5 is in R2, then taking their direct sum is stacking them on top of each other, forming 1, 2, 3, 4, 5 in R5. The symbol of this operation is basically a plus sign inscribed in a circle. The direct sum of two vectors of dimension n and dimension m has dimension n plus m. Now if we want to define the direct sum of two vector spaces, capital U and capital W, of which the direct sum is a vector space capital V, every vector in capital V is a direct sum of two vectors in the vector spaces capital U and capital W. We sort of add some attributes of the original to the other vector space. And to do this, we need to have a concrete set of elements that represent each vector space as a whole. For example, the direct sum of a plane with the two basis vectors we normally use and a line with just one basis vector is our normal three-dimensional space, R3. To take a direct sum of vector spaces, create a new space with the basis vectors of all the subspaces. We can also take a direct sum of matrices. We can consider matrices to be elements of vector spaces as well as vectors. A good question to think about is why? When we take the direct sum of two matrices, we want their dimensions to add up. You can do it like this. If you have two matrices A and B, then their direct sum will look like this, where the entries marked A and the entries marked B are the entries of the matrices A and B. As you can see, the dimensions add up. An example with actual matrices would look like this. The symbol for the direct sum of matrices is the same symbol that's used for the direct sum of vector spaces. Now let's consider something that, at least in my opinion, looks really cool: vector fields on manifolds. A vector field on a manifold assigns to each point on a manifold a vector. For example, for some manifold M, we can consider the tangent vectors to each point on the manifold. In this case, we can call the manifold a quote-unquote hairy manifold, and we can quote-unquote comb the manifold by swiveling the vectors around that point. Any specific configuration of all these vectors is a vector field on the manifold M. On a two-sphere, that is a two-dimensional sphere, remember our definition of dimensions on a manifold, we can't comb all of these without leaving a bump of quote-unquote hair somewhere. We can say that the vector field disappears here. There is in fact this really cool theorem called the hairy ball theorem. I'm not lying, it really is called the hairy ball theorem, which states that any vector field on an even dimensional sphere has to vanish somewhere, aka you can't comb it without leaving a section that can't be combed flat. On odd-dimensional spheres, such as the 3-sphere embedded in 4 dimensions, or 1 sphere, what we know as a circle, we can comb everything flat. We can in fact generalize this to things that are not spheres. For this, we use something called the Euler characteristic. The Euler characteristic is calculated for a graph like this or a polyhedron like this using the number of vertices minus the number of edges plus the number of faces. For any convex polyhedron, this is equal to 2. This formula, v minus e plus f equals 2, is also known as Euler's formula. Side note, remember that the graph has a face which you might not be thinking of, the unbounded face. For figures other than polyhedra, you can find Euler's characteristic, usually denoted by x, by using what we call a polygonization of the figure, which we won't be covering and you can research more about. We can also use homomorphism if it is applicable. What this means is that if we take a cube, calculate its Euler characteristic 2, a sphere's Euler characteristic is also 2, because a sphere is topologically equivalent to a cube, i.e. they are homomorphic to each other, meaning you can distort one into the other with no ripping or cutting. The main thing to remember is that if something has an Euler characteristic of 0, then it has to be combable. Here are some examples of some Euler characteristics I found on a table in Wikipedia. A sphere, for example, is not combable. We have established that already with the Hairy-Ball theorem, since it has an Euler characteristic of 2. As you can see, a torus does have an Euler characteristic of 0. Therefore, we can expect it to be combable. A vector field assigns a vector to each point on a manifold. On the other hand, a sheaf assigns a vector space to a point or subset of that manifold. Suppose we have an arbitrary topological space X. We first have to get comfortable with the idea of stocks, or vector spaces on subsets, and only after that can we examine if we can fit all these stocks together to form a cohesive whole. Let's do a simple example where a topological space is a space of real numbers, or R. Before we continue, I would like to remind you that we can consider an infinitely large group of functions to be a vector space, because just like vectors, we can add, multiply, and divide functions. They're sort of vector-y things. Moving on, we can define the stock of a subset of R to be the group of functions that take a subset of R to R. Unlike your school's algebra class, a function here should be more thought of as somehow changing that subset of R into the entire space of real numbers, R, even though it does have one input and one output. If we call our subset U, we get this. What that basically says is that the stock of our subset is defined as all the continuous functions that go from that subset to the space of real numbers. Since our subset is a subset of the real numbers, what we are once again saying is that we define functions that take a subset of R to R, and we define the stock, or vector space, of that subset to be the group of continuous functions like these. There are infinitely many of these functions, but this is an example of some of them. Now imagine we also have some subset V of U, a subset of a subset, so to speak. Take all the functions in U and restrict them to V. We basically make a smaller section of that earlier section of functions. What this notation basically does is to define a morphism, which is basically a transformation that takes a stock on U and restricts it to V, turning it into a stock on V. You might wonder why we're doing this, since it seems kind of pointless, but consider the fact that smaller and smaller subsets have to fit together cohesively for us to construct a sheaf. To understand what we mean, we can look at a case where they do not fit together cohesively. If we restrict from U2 to U1, this section for a specific function f does not work. When acted on by the restriction map from U2 to U1, the f doesn't go down to a smaller section of it. Something that actually does fit together looks more like this. We require that every single set on every single function looks like this for our sheaf to work. We also need a few other properties, like if we have two sets A and C, and you have a function f, your result from restricting it from A to set B, and then from B to C, has to be the same as just restricting from A to C. If you have two sets A and C, and you create compositions of restriction maps of a specific function that goes from A to C, whatever middle set you use, your result has to remain the same. For two sets u1 and u2 and their intersection u12, the result of taking our function f specifically on u sub 1 and then using the restriction map from u sub 1 to u sub 12 should have the same result as taking f and using on it the restriction map from u sub 2 to u sub 12. A stock that does not follow these rules is called a presheaf. If our stock does follow all these rules, we have defined a sheaf. Our global space of functions is all the continuous functions that take real numbers to other real numbers. Since all these subsets add up to the total space R for the specific example, our entire sheaf globally defines the vector space of all the functions from R to R. We can write this sheaf like this. Now, you might ask, originally we said that a sheaf assigns a vector space to each point on a manifold, not to a subset. However, consider the fact that an infinitely small subset can just be considered as a point, so our original statement is still valid here. Keep in mind that we could have defined a sheaf on any topological space. We just did it from R to R because those functions are easier to draw. If you want to learn more, I would really recommend researching more about sheaves online, since we're only just touching the tip of the iceberg here. Now we get to the exciting part of this video. We're going to see how all the properties of manifolds we've described so far change when we combine them. One way to do this is the direct product. Direct products take both manifolds and make another manifold with both of their coordinates. For example, the product of two lines is a plane, and the product of a line and a one sphere or circle is a cylinder. The cylinder has two coordinates. One is the angle of the circle, and the other is the position on the line. A torus, or a donut shape, is the product of two circles. Keep in mind that we're talking about only the surface of the donut shape. A product of two manifolds is similar to the direct sum of vector spaces. You add new coordinates to what you already have. The torus has the angle on the quote-unquote inside circle and the angle on the quote-unquote outside circle as its coordinates. Now we will consider products of Lie groups and products of Lie algebras in a way that is less connected with geometry. We'll have to use mainly analytical methods to analyze these. First, we will consider our old friend SO2. SO2, as we have learned, is the group of rotations of a circle. It is also, consequently, the group of rotations of the entire 2D plane. It preserves distances. Let's consider SO2 from a different perspective. We can write each element of SO2 as a matrix, and that matrix will generally have this format. Here, R represents any rotation, or any element in SO2, by an angle theta. Now let's look at the Lie algebra of SO2, which we will denote by SO2 in lowercase. We already know that it is this tangent line. Let's consider it from a different perspective. The Lie algebra of SON turns out to be the group of all n by n matrices that if you flip them, or take their transpose, that would be the same as taking the negative of every term. The Lie algebra of SO2 can therefore be written like this. A generator of this Lie algebra is a matrix that when multiplied by any number can make anything else in that Lie algebra. A possible generator of this Lie algebra could be the matrix with 0, -1, 1, and 0 as its entries. We could define any generators that fit these criteria, just like we could define any basis vectors for a 2D plane. It's just convention to use 1s and 0s for our generators. We'll call our generator O sub 1. Now we consider a group called SU2, the group of 2 by 2 unitary matrices with determinant 1. A unitary matrix is a complex matrix which has its inverse be the same as its conjugate transpose. What this means is that a unitary matrix's inverse can be found by flipping the matrix over its diagonal, the transpose, and then taking the complex conjugate of each entry. This is how we would write SU2 in matrix form. Take a moment to pause and ponder why the absolute value of a squared plus the absolute value of b squared has to equal 1, and what that has to do with the determinant being 1. The Lie algebra, as it turns out, of SU2 is a group of all skew Hermitian matrices with trace 0. The trace of a matrix is basically the sum of all its terms on the main diagonal. We can write the Lie algebra of SU2, which you denote by SU2 with the letters lowercase, like this, has its conjugate transpose be equal to taking the negative of every term. Now let's look at the generators of the Lie algebra of SU2. A weighted sum of these generators results in any element in the Lie algebra of SU2. Remember that we are talking about complex matrices here, so we actually have 3 generators. This is an example of them that fits our requirements, which it means it suits the format shown above. Side note, the Lie group SU2 is actually the group of unit quaternions. While we won't be talking about those in this video, if you want to learn more about them, there are a lot of great resources online where you can do so. I strongly encourage you to check those out. Now, coming back to our original topic, since Lie groups are the marriage of the concepts of manifolds and groups, we can take the product of 2 Lie groups just like we took the product of 2 manifolds. Though these groups are hard to imagine spatially, we can still use matrices to do this. To take the product of the 2 Lie groups we described earlier, SO2 and SU2, we can use the direct sum of matrices. Let's call our new Lie group Z of 2. The Lie algebra of a product Lie group is a direct sum of the component Lie algebras. Taking the direct sum of our Lie algebras, we get this. We can now define generators for our Lie algebra matrix. Here are some examples. We will use our original generator for the Lie algebra of SO2 in the upper left, and we'll make 3 matrices, each with a different generator of the Lie algebra of SU2 on the lower right. I'd like you to remember that taking the product of 2 manifolds can be order dependent. For this example, it depended on which matrix we put at the top of our direct sum and which one we put on the bottom. To see this more clearly, here we can see that matrix 1 does not equal matrix 2. This means that the direct sum of matrices is not commutative. Now let's move on from that and consider vector fields on product manifolds. The example we've been using a lot so far, a torus, will work fine here. Any vector field on a torus can be broken down into 2 vector fields, each on one of the circles. For example, this specific vector on this vector field can be broken down into a vector on the inner circle and one on the outer circle. The vector field on a product manifold is essentially the direct sum of these 2 vector fields. Try thinking of a vector field as the function between the manifold and vector space, as each point on the manifold gets its own vector. Taking the direct sum of 2 vector fields can be thought of as adding new dimensions to that function. We're basically taking each vector in that vector field and adding new dimensions to it. Any vector p on the torus can be thought of as the direct sum of 2 vectors w and v on these 2 circles. The vector field on a product manifold is the direct sum of the vector fields on each of the separate manifolds. How does combability change with a product manifold? Since a circle, or one sphere, is combable by the Hairy-Ball theorem and has an Euler characteristic of 0, then the product of 2 circles, or torus, should also be combable. Though we won't be proving this, the Euler characteristic of any product manifold is the product of the Euler characteristics of its constituents. Since a circle has an Euler characteristic of 0, then the Euler characteristic of a torus, which is the product of 2 circles, is also 0, since 0 times 0 equals 0. Now let's consider the product of a disk with Euler characteristic 1 and a circle with Euler characteristic 0. Remember the difference between a circle and a disk. A circle is just a boundary, while a disk is filled in. So a vector field on a disk might look something like this. A disk is not combable because it has a non-zero Euler characteristic. The product of a disk and circle is a torus with the cylinder part filled in. Multiplying the Euler characteristics, 1 times 0 equals 0, means that this filled-in torus is combable. If the vector on the torus has its component vectors be a 0 vector on the disk and an existing vector on the inner circle, the direct sum will still exist, so that point on the torus will still be combable. The yellow vector is an example. Remember that we are not just talking about the surface here. We are talking about combing little hairs on the insides too. This is an example of a vector field like that. Now let's end with considering sheaves on product manifolds. As with vector fields, we'll try and decompose our sheaf. If our product manifold is R2, which is composed of R and R, as we did before, we can define the stock of a subset of R as a set of continuous functions that take that subset of R to R. If we can make this fit all the rules, then we will now have a sheaf. For each of the R's, we have this sheaf. We can consider these subsets taken together, forming what we can denote by U2. Since each U had its own stock or vector space of functions, then taking the direct sum of these vector spaces results in this. That is, for any product manifold, its stock is the direct sum of the stocks of its constituents. If our stock is F, and we have two manifolds M and N, then this fact will be written like this. If all our stocks form sheaves that follow all the rules, we will now have a precise definition for a sheaf on a product manifold. Now, to wrap up, a common theme we've noticed across a lot of our examples is that we're taking a property of a product manifold and breaking it down into parts. That's something mathematicians do a lot. It's part of the mathematical way of thinking. Learning math doesn't just allow you to discover new and fun things, but it also develops your problem-solving skills. Also, math is just elegant, sometimes even beautiful. I hope you saw that with this video, and we'll continue exploring math. Have a great day!